Okay guys, let's take a look at our lesson for today. We're going to be looking at applications of differential equations. This first lesson should be very familiar to you with exponential growth and decay. We worked on this in pre-calculus. So in exponential growth or decay, we assume that the rate of increase or decrease of a population at any time t is directly proportional to the population. That directly proportional, inversely proportional, those are some algebra concepts that hopefully you recall. Directly proportional, if you remember, is just straight directly across the equal sign. So this is the differential equation that we use for growth or decay, where k is a relative growth rate. Okay, so this is a vocabulary word. Sometimes they're going to ask you for the relative growth rate. And if you don't know they're talking about k, then you're really not going to know how to answer the question. So k is the relative growth rate. The general solution to that differential equation is this equation, which should look very familiar to you. In fact, some of these problems you can just have memorized that equation and plug right into it and go on and not have to solve the differential equation. I'm actually going to, on this first couple, we're going to solve the differential equation just so you see it worked through. But if you want to skip directly to here and skip a couple of steps, you certainly could. So let's see. So we have the rate of change of y. So the rate of change of y is proportional to y. So that's our setup for our differential equation. We're going to separate the variables. So I have dy over y equals k dt. We're going to integrate ln absolute value y equals kt plus c. This should remind you of that lesson last week, that differential equation day 2. We worked a lot with natural logs. So we solve for c right now. If I put a y of 2, so let's see, when t is 0, y is 2, so I have ln 2, so c is ln 2. Then if you recall, we put that back in, so natural log y equals kt plus ln 2. We solve for y, so e to the kt plus ln 2 equals y. Now remember the simplification that we did last week, where we know that's going to be 2e to the kt equals y. Now I want you to notice where we are. See this equation right here and this equation right here? P naught is the initial condition, and our initial condition was 2. Notice there's a 2 right there. And then we have e to the kt equals y. So you could take all of this and just skip to here. If you remember the differential equation, if it's exactly like that, then that is a fine thing to do. All right, so now maybe we remember from pre-cal we have to find k. So this is where we use the second condition, t equals 2, y equals 4, to find k. So let's do that. So let's see, y is 4 equals 2e to the k times, and our t is 2. So I divide both sides by 2, and I get 2 equals e to the 2k. I natural log both sides, and I get natural log of 2 equals 2k, or k equals ln 2 over 2. Yes, you could do some fancy logarithm rules with that, but since you're just going to put it in your calculator, you don't have to. So our equation is going to be y equals 2e. Since I've already established what k is, I can actually in my equation just write kt. I don't have to write natural log 2 over 2 over and over again. Since I've equated k to natural log 2 over 2, then this is perfectly fine. So I want to know what happens when t is 3. So y equals 2e to the 3 times k. So I'd use my calculator. I would substitute 3 in for t, and that would give me a value, y equals 5.6568. 5.6568. And that is our very first exponential growth problem. All right, let's look at the second problem for today. So we have, suppose that 10 grams of the plutonium isotope Pu-239 is a half-life of 24,100 years. Let's see, was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? All right, so I am going to actually start on this particular one. I'm going to start here at the equation. I'm not going to go back to the differential equation just for time's sake and because we can. All right, so I've got to calculate what K is. My condition that I'm going to use is, my initial condition is 10, and we're told the half-life is 24,100, so that means that takes that long for it to halve, so half of 10 is 5. E to the K times, and the time is 24,100. So that's 10 e to the K times 24,100. So I can, solve. I can move the 10 over. I get 1/2 equals e to the 24,100K. I can natural log both sides, and I get natural log of 1/2 equals 24,100K. So K is natural log of 1/2 divided by 24,100. Okay, now that I've said what K is, I don't have to write this really long thing anymore. I know what K is, so I'm going to move on from there. And let's see what it wants. It wants to know how long will it take for the 10 grams to decay to 1 gram. All right, so we have 1 equals 10 e to the KT. Again, we know K is this right there. So I put that in my calculator and I solve, and I get, well, there's a couple ways. Well, I'll solve by hand first. There's several ways to do it in your calculator, but if we're just going to isolate t, I would do divide by 10, 1/10 equals e to the KT. I would natural log both sides. Natural log of 1/10 equals KT. And then I would divide by K. So T is going to be natural log of 1/10 divided by K, which we have right up here. All right, and so then what we would get, we'd get T equals, let's see, what is it? T equals 80,058.467 years. Well, that's a long time. Okay, well, since the half-life is 24,100 years, we would expect our answer to be quite large, and it is. All right, so that is applications using exponential growth or decay. We have one more topic to look at, and that is Newton's law of cooling. It's on the next slide. If you would go over there with me. This is probably reminiscent of pre-cal as well. So Newton's law of cooling is the rate of change in temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So that is our differential equation for Newton's law of cooling. All right, so let's tackle this problem. Suppose a room is kept at a constant temperature of 60 degrees. Okay, so that's our surrounding temperature. And an object cooled from 100 degrees to 90 degrees in 10 minutes. How much longer will it take for its temperature to decrease to 80 degrees? All right, so our initial condition at t equals 0, we are at, so little t is time, and then big T would be 100 degrees. That's our initial condition. So let's use our differential equation. Let's plug into it. So I have dt over dt equals, we don't know the growth rate, we're going to have to calculate that. Temperature of the object changes. We can't put a number in for that. No number in for the object because it changes. Minus the temperature surrounding medium or surrounding air is 60 degrees. Okay, so that's our differential equation. Times, and we have our K right there. All right, So now let's separate our differential equation. So we get dt over t minus 60 equals kt dt. We integrate both sides. Natural log absolute value t minus 60 equals our, oops, this one was just a k. Let's fix that little guy. That was k dt, so when I integrate it, it's kt plus c. All right, so now we are going to solve for c. Let's see. So we have in 10 minutes, it went to 90 degrees. So that's my next one. So when t equals 10, I'm going to write my equation in terms of minutes. You can write your equations as hours or minutes. You just have to decide, and unless it tells you, you can pick. Since we're using minutes, I'm writing it in minutes. At t equals 10 minutes, our big T is 90 degrees. So using that information to solve, we can actually have two pieces. I'm going to use this information to solve for C. When t is 0, little t is 0, big T is 100. So I have natural log of 40 equals C. So putting that back in, ln absolute value t minus 60 equals kt plus ln 40. We solve for big T. So e to the kt plus ln 40 equals t minus 60. Recall this ln simplifies basically, and we're solving for t. Hopefully this isn't too stressful. I'm going to do a couple of algebra steps at once. I'm going to move the 60 over, and I'm going to simplify this to 40. So big T should equal 60 plus 40e to the kt. All right, fantastic. So now our job is to solve for k. We're going to use our second point right here to solve for k. So big T equals, actually we're going to use this point, so it's going to turn big T into 90. So 90 equals 60 plus 40e to the k, and little t is 10. All right, solving for k. I would subtract the 60 over and divide by 40. And that gives me 3/4 equals e to the 10k. Then I natural log both sides. And then I solve for k. So k is going to be the natural log of 3/4 divided by 10. Okay, so now that we have k, which is the natural log of 3/4 divided by 10, I know what k is. I'm not going to write it over and over again. And I'm going to use that to answer the question. Now we want to know how much longer, this is a key word, how much longer will it take for the temperature to decrease to to 80 degrees. All right, so we have our formula, and we're going to set it equal to 80. 80 equals, then we have our formula, which is 60 plus 40e to the kt, and we know k is that. So I solve, and I get, and I'm not going to go through what we do is we subtract subtract the 60, get 20. 20 divided by 40 would be a half. So we have 1/2 equals e to the kt. Again, k is this value. And then we solve, and we get, by taking the natural log of both sides, etc., like we have done several times before today, we solve and we get t equals 24.094 minutes. Now, some may say, oh, okay, I'm done. It's 24.094 minutes. But we need to make sure that's what they asked us. They said, how much longer will it take? So they're not talking about from the initial time. They're talking about it's already been 10 minutes. How much longer is it going to take for the temperature to decrease to 80 degrees? So that means I have to subtract 10 from this time. And my actual answer is going to be 14.094. So 14.094 minutes longer. All right.